Hi, welcome to Traxic Computer Science. This is the part 1. We're going to learn about foundations of computer science for AI product managers. Let's dive in. This is going to be a long session, so we will split it into two sessions, part A, part B. And what we are going to look at in part A is about why a PM should learn computer science foundations. Then we are going to look at data structures like a big O notation, array and contiguous memory that we learned in the last session. Then we're going to look at linked list. I keep saying LinkedIn. Then we're going to look at linked list, how data structures are linked to each other, stacks, how data can be stacked on top of each other, like you stack plates on top of each other. Then we're going to look at queue, how people stand in a queue at a Starbucks to receive coffee, hash table, how you can assign hash values for a given data and how fast it is to retrieve data. Then we're going to look at tree structures on how to retrieve data when data is stored in a particular tree format. We're going to use similar trees in algorithms as well when we do BFS and DFS. Then we are going to look at graph. Graph is very much important for understanding how your data is stored in vector databases. Then we are going to look at heap or priority queues, and finally a cheat card that shows how all of these data structures can be put on a complexity graph to understand how growth of certain data will impact the performance of these data structures. In part 2, we are going to look at algorithms like sorting, searching, breadth first and depth first search. We are going to look at dynamic programming, how we can um, uh, calculate or save what we have already done and need not redo that again and again. That's something we're going to look at dynamic programming. Then we're going to look at greedy search or greedy travel algorithms. And finally, complexity, big O notation that we are doing on day 0. We are going to do a deep dive on how it impacts an AI. Finally, we'll conclude with PM perspective, the engineering negotiation that we should be ready to do. And last but not least, the interview prep with some questions that interviewers might ask AIPMs on this topic, which is computer science foundations. The first topic that we're going to talk about is why should a PM learn about computer science foundations? Yeah, I believe it's very necessary. And whenever we get into conversations with product managers, other product managers, and other engineers, it's very important to understand the decisions being taken, the constraints being put in, the uh, performance improvements being expected, and so on. And this will only happen if we understand how these algorithms, these data structures help us build features or build products in the first place. Let's start with understanding that we will never be asked to write algorithms. That's very clear. Product managers are not being asked to write algorithms. But what would we be required? Yeah, we'll be required to translate a requirement into a cost shaper. Imagine there is a requirement being written by us that a instant search across 50 million docs needs to happen. Yeah, it's a demand for sublinear lookup, which forces us to understand how the data will be embedded, how the indexes will be created, and will this be a build time decision or will there be staleness of data. All this must be part of the requirements. Yeah, and you should be good at smelling a scaling wall before you hit it. When we are building something, you need to take care of the growth of users, the documents, the tokens, the number of tool calls that will happen. If you don't do this at design time, somebody is going to call you at 2 a.m. in the night. Yeah, you either be ready to wake up at 2 a.m. in the night or better do this on day 0. You should also be ready to call the bluff in both directions. Sometimes it won't scale. Yeah, it's real. It cannot scale beyond a certain time. Sometimes it's a premature optimization. We start thinking about huge volumes, huge requests that are going to come and start to optimize it in the beginning itself. So we lose 3 sprints of actual work and we try to optimize, which could have been done better. Yeah, finally it's the pricing of the system. Every cache, index, or patch decision that we are going to take is all about money. Okay, and understanding the complexity behind all of these products or tech is all about cost literacy. If you do not understand the complexity, you do not understand the cost literacy. So what's the mantra here? What grows and how does the cost grow along with it? That has to be asked relentlessly, because that's 80% of the value that a product manager brings onto the table. So first we are going to look at or understand something called Big O primer. We'll understand what is a Big O notation, because that's the vocabulary we'll be using across with engineers, with ops teams, with the CFOs, whenever a conversation about cost comes. Okay. So going forward, there is something called asymptotic notation. Okay, computer scientists, whenever they try to analyze algorithms and their performances, they go by something called asymptotic notation. Okay, what is an asymptotic notation? A mathematical shorthand that describes how the execution memory or the memory usage of an algorithm changes as the input size grows towards infinity. Okay, as your data, as your requirements or API calls or your token usage, all they increase exponentially or linearly towards infinity, what happens with the execution time or the memory usage? That's what asymptotic notation helps us to do. And computer scientists typically use three notations, which is big O, big omega, and big theta. So whenever algorithm is working and we try to input the data, there are three types of scenarios that we are going to hit. One is the worst case scenario, one is the best case scenario, one is the average case scenario. Okay, big O represents that worst case scenario or upper bound. It guarantees an algorithm that it will not take longer than its upper limit. Okay, so that's the ceiling. Okay, then you have your big omega, which is at the bottom or lower bound, and it tells that no matter how much data you give it, this is the lower bottom that it will not cross on the lower side. This is the bare minimum that we need. Then we have big theta in the center, and that's the average case scenario or tight bound. It exactly describes the growth rate when upper bounds and lower bounds match, but it's really not helpful. So many of the times you will only see big O notation, and even in this session that we are going to run through, we are only going to look at big O notation. Why big O and not the big omega and big theta? Because big O notation helps us with worst case guarantees. Imagine a software that's running and suddenly there is a peak load. It should handle without crashing, and big O defines that maximum resource an algorithm will ever need, ensuring that system can handle the worst case scenario. Secondly, it helps as a real world inputs. Best case scenarios are good, but they are rare and they are unhelpful. For example, sorting an array which is already sorted takes almost no time. But optimizing for this rare event does not really help when the data is completely randomized. So real world inputs are more not on the best case scenarios, they're on the worst case scenarios. Mathematical simplicity. Big theta requires proving both the upper bound and lower bound. Big O is much easier to calculate mathematically because you only need to prove the upper limit. You don't have to calculate the mid or the lower bound. Finally, the industry standard. Because tech companies care most about system failures, engineering cultures and interview loops default to Big O. It creates a shared high stakes language for performance across teams. And as we rightly understood, one thing that we need to keep in mind is Big O notation is describing the growth and its uh, performance when the growth is happening, not the exact execution time it takes. Okay, we'll discuss more of this in a slide, but let's understand this in terms of examples. Okay, let's say Big O notation is given as O of n. Okay, the order of n. Okay, when we search an array, for example, okay, we're talking about the number of elements that we can search for in an array. For example, let's say we are searching for n equal to 5. In an array, if there are 5 elements, the order is 5. Sorting a list of n, traversing a graph, n could mean the number of vertices. Processing a string, number of characters. For example, if you're trying to understand the number of characters in a string, or trying to manipulate the reversal of characters in a string, or find the length of a string, and so on. Okay, matrix operations, when you try to do matrix multiplications, like we spoke in the last session on how how systems do matrix multiplication on dot product to come up with the system requirements for data storage, for compute, etc. And we saw that matrix multiplication is everything in data science and AI/ML. So here n would represent the number of rows and the number of columns, okay? And n is the size of the input to this algorithm. How much data are we going to use? How much data is going to pass through? And common notations on one card, something looks like this. If it is a constant, basically there is one array element in index, we will access, or it will be a bigger notation of O of 1. If it is logarithmic, O log n. If it is linear, O of n. If it is an array, it is O of n, okay, because it scans every element in that array to do the process. Then there is something called O n log of n, which is linear arithmetic. It is used to do merge sort and heap sort, where you are continuously splitting the elements by half and then trying to sort the remaining half. Okay, that's how the merge sort and heap sort work. Then you have quadratic, cubic, exponential big O notations. Then you have factorial, O n factorial, that generates all required permutations for a given one. Yeah, from the top as you read to the bottom, it is a danger gradient. Okay, everything about this is comfortable. The systems can take care of processing or understanding the growth very easily. Everything below this is a design conversation that we need to have with engineering team. For example, if you have a loop dependent on another loop, where all elements are to be compared with all elements in another array or something, then it is a quadratic equation, quadratic compute, and that will take a big growth of O n square. So that conversation needs to be had there. Okay, and coming to the actual notations on how this work. For example, you're trying to access a particular element O of an array of 4, its position is 4. So no matter whether the array element has 10 elements or 10 million, you'll only be targeting by the number of same operations, which is 1 operations. Why? It doesn't matter how many elements you have in the array, because you have the index, you'll always access it by 1. But if in that array you're trying to print all the elements, you need to go one element at once. Okay, the work grows proportionally with n. So in that case, you'll have multiple operations because you'll have to go through all of them. So in array, O of n is the big O notation for arrays. Yeah. See, if the loop count is tied to something that grows with your product, like documents, users, tokens, you are in this linear territory. Yeah, the growth is linear. Yeah, and the growth curve is now a product question. Hey, how much will it grow by in a week? How much will it grow by in a month? How much will it grow by in a quarter and a year? That's the question that a product manager needs to answer, because correspondingly, engineering team will take a decision. Yeah. Now look at this. We have quadratic equation here, which is O n square. Like we discussed earlier, if every element of a particular array needs to be compared or accessed with another element in another array, for example, if you're trying to print a matrix, okay, for every element in a particular row and every element in the column needs to be printed, this will run O n2, n into n, okay, n square. So the inner loop runs n times for each of the outer n iterations. So if you see, suddenly the number of operations is growing. In the previous one, we saw that it's just 5, 10, 500 and 1000 operations because it was linear. But now since you're trying to compare, it's 25, 10,000 and 1 million operations that we are trying to do. Let's take a log n logarithmic big O notation. If you're trying to do binary search, we'll come to this in the binary search algorithm. But imagine you're trying to do a log n, yeah, log of 16, which is 2 power 4, 16, which is only 4 steps. Okay, now if you do a log of 1024, you'll get 10. Okay, that's the only number of steps needed to reach to the element. Okay, now compare these two, left and right. Okay, quadratic on O n2 and O log n. At a million items, quadratic equation is a trillion operations and logarithmic is only 20. Almost every architecture decision that you're going to take as a PM is moving from left to right. Yeah, instead of doing a million or a trillion quadratic operations, can you reduce it considerably and hence improve the performance of the system? That's the question product managers will always be asking. And you might ask, hey, why are constants being ignored? Yeah, that's because as n becomes very large, they grow at the same linear rate. And big O notation describes the rate of growth, not the exact runtime. That's why we drop always the n, we only retain the other operations. Yeah. Intuitively also it's very easy to understand. O of 1 is open directly to the correct page. Yeah, if you're looking at it as an example, O of 1 is like opening directly to the correct page. For example, if you open a book, you open at O of 40 page. Yeah, but what if you want to search for a particular word, and the numbers are all sorted in a particular sequence? Okay, then what would you do? You would split the big array into two. Yeah, you'll open in the middle and you'll compare, saying that is the number in the left half or the right half. So with log n, you're always eliminating by half. Yeah, and read every page one by one is O of n. Like we saw, every element, if it needs to be accessed in an array, it is O of n. If you're looking at quadratic, it is O n square, comparing every page with every other page. Yeah, it is 2 of n if we are trying to do every possible combination. Yeah, every two elements, if you try to combine every possible combination, it will be O2 to the power n. And O n factorial if you are trying to possibly do the ordering. Yeah, 1 comma 2, 2 comma 1, then you have 1 2 3, then you have 2 1 3, then you have 3 2 1, then you have 1 3 2, like that. If you're trying to do all the possible orderings, then it will be n factorial. Yeah, while n is the input size, big O describes how time or space scales as n grows. It doesn't actually do the runtime calculation, it only says how will be the rate of growth. Data structures. We are going to look at 8 data structures and how data is stored, and based on the accessing of those data structures, we'll do a big O notation for the worst case scenario, and we will understand how it will apply to our AI tech stack or AI stack that we are going to work on, and some of the questions that we are going to collaborate or discuss with engineering team. Yeah. Array or contiguous memory. We saw in the last session that tensors are nothing but arrays. Yeah, we looked at 2D, 3D, 4D tensors also in the last sessions. If you have not looked at that session, please go back and read that session and come back, because we're going to be referencing a lot into our existing sessions. Okay, so array is just a block of memory holding elements back to back. Okay, if you had to find the address of an element, all you have to do is find out the base plus index into element size. You only do two operations, you do a multiply and an add. There is no searching required in this. Okay, so the big O notation is always O of n. Okay, the mental model, if you would like to think of it about like a row of numbered lockers that you have. If you know the number, it's instant. Otherwise, you will have to stop at every locker, look at it and say if this is your locker or not, and then open everyone, look at the data, and then go until your data. Okay, so it's in simple O notation, it's always O of 1. If there are n elements that we have to iterate through, it becomes O of n. Okay, all the model weights, the embeddings, the image batches are all contiguous numerical arrays, and GPU throughput or the performance of a GPU depends on this batched or coalesced access. We'll understand this deeper in the next slides, but if all the data is together in a continuous array of elements, it's easier to perform the operations rather if they are in different addresses. Yeah, that's what we are trying to say. And this is why deep learning use dense arrays, which are very compact, packed together in a sequence of addresses, and not linked structures where the address of one points to the other and so on. Okay, iterating against the layout thrashes cache 10 times slower for identical math. That's how different it becomes. Okay, in between knowing the array's address and not knowing the array's address, there's a huge difference. Okay, we know that arrays are laid out by row by row or column by column, and if you had to iterate the layout, it will become 10 times more more time consuming that way if you didn't know the address. Okay, now for PMs, here's the question. Hey, if there is a dense array and there is a pointer chasing like linked list, which would you choose? Okay, in dense arrays, the performance is fast, but it is memory hungry at the same time. How much memory? Suppose you have 100 million documents that needs to be searched through, with each document having 1536 dimensions, and every number in that is a float 32. In that case, we are somewhere looking between 600 GB of RAM, because we'll have to search on this dense array. Yeah. Moving ahead, we wanted to discuss about what is a coalesced memory access and why the contiguity matters, and why it is fast as well. Imagine you have 32 threads that are trying to access certain elements that are placed in addresses that are in sequence. Yeah, the 32 reads would only need one memory transaction, because if I know the beginning, I know the rest. It's easier. Yeah, whereas in a non-coalesced or a linked list manner, I have to go to 100, then I have to point to a different one, then come back to this, then come back to that. So there is a lot of address chasing or address scatterness that's happening here. Yeah, and imagine 32 people are trying to fetch books. Yeah, if all the people are all the books are on one shelf, I only need to make one trip. But if they are not, I will have to go one floor at one book, then identify where is that second book, then go to that floor. There are multiple trips involved here. Yeah, and that's where GPUs come into play. Yeah, GPUs execute threads in groups called warps, especially NVIDIA's architecture or hardware architecture is, or semiconductor chips that they have built is dependent on this architecture, where 32 threads are clubbed together and all of them executed in together. And that's what is the smallest unit of execution for NVIDIA as well. It's called warp, and it has it's a collection of 32 um, threads that are executed together. Imagine you have 128 threads coming in, and there are 4 GPUs that each handle 32 threads. Yeah, not 128 independent threads, but 32 of them run the same instruction on the same data. Yeah, that's how the parallel processing happens. And we will not look at the rest because it's going to be a little more complex. All we need to understand is that threads, if executed in parallel with the same instruction but different data, NVIDIA provides that capability, and hence it's faster. Yeah, why 32 matters? Scheduling or memory coalescing and synchronization are all managed per warp. So that's how the performance is achieved there. Now, many of you would have asked, hey, I understand CPU, the central processing unit that we get with Intel or anything that sits in my computer, but what is a GPU, the graphic processing unit, and what are the differences between these two? Okay. CPUs are typically designed for fast and sequential processing of diverse tasks. For example, if you're doing a task A, then you want task B done, then you want task C done. All of that can be done in sequence, and CPU is pretty good at that because it takes that task, gives all the memory to it, and gets it done faster. So sequential processing of events is faster there. But with GPU, we learned in the last session that we need to do hundreds and thousands, millions of matrix multiplications in parallel, because LLMs are nothing but matrices of weights, and input is nothing but input of array of elements that need to be multiplied with this array of elements in the matrices or LLMs, and the output is the token that we get. Okay, so we need to do millions, if not millions, at least thousands and thousands of matrix multiplications, and that's possible through parallel processing only. You can't do sequentially. And to do that small massive parallel tasks or repetitive tasks, GPU was built. Initially, NVIDIA built these graphic processing units for gaming, but later extended when GPU was used in the AlexNet competition of ImageNet. If you remember the ImageNet from the history of AI sessions that we did earlier, if not, please go through that. That has a very interesting segment where we talk about how GPU came into picture and how NVIDIA understood that the future is all going to be about compute power for AI, and how they pivoted from gaming into AI. Okay, so CPU is actually executing only few powerful threads, where GPU is very powerful for executing lightweight threads, but thousands of them. Okay, CPU works on scheduling individual threads. This works in a collection of 32 threads. This is optimized for low latency. This is optimized for high throughput. Throughput as in, imagine it like a bandwidth. We want 2 Gbps, 3 Gbps of bandwidth for our internet. Similarly, GPU is processed for the number of calculations per second. How many calculations can it do in per second? Okay, this handles different instructions efficiently. Here, Warp executes the same instructions on different data set. Okay, that's what it's optimized for. So the question that might be asked is, hey, why are GPUs fast for AI? Because the core operation is dense matrix multiplication over contiguous arrays, and GPUs pair thousands of cores with memory designed for coalesced access to adjacent addresses. That's why the GPUs are very powerful. This brings us to one of the topic that we left there. We said, hey, we need 600 GB of RAM, but we never got into the details. Okay, this slide explains that. Imagine you had 100 million vectors that you had to embed and then search. Okay, and imagine each vector need to have a dimension of 1536, because if you remember, each token can be taken and embedded in the space of 1536 dimensions, and that's how we will remember what's the position of that token and so on. Okay, so imagine if there were 100 million vectors into 1536, we will need 153 billion float numbers, and each float we are looking at 32 bits, which is 4 bytes here. If you multiply this, we approximately get 614 GBs, or 614 trillion bytes, which is like 614 GB, approximately 600 GB. Yeah. So the formula that we are going to come up with is, hey, if you want to calculate the memory given a number of vectors, the dimensions, and the bytes per value of each of that weight or number in that array or matrix or dimensions or vectors, this is how we think about it. Number of vectors into dimensions into bytes per value. Okay, very important formula, because every time we have to do calculations on how much data needs to sit in RAM or storage space and all, this is how we are going to look at it. Okay, and if your vector database is all about embedding and storing documents, this is how I'll calculate the size of the database. Yeah. Why should a PM care? That number alone dictates the architecture. Yeah, it is a difference between this runs on one machine versus this is a distributed systems project. Do I need to bring in systems that will hold 10 GB or 600 GB or 1 terabyte, 1 petabyte? How much data do we need? Yeah, all that will dictate the architecture. So we need to understand this. Yeah. And one thing that we were discussing is, hey, if it is float, we use 32 bits, right? It's a huge thing, because approximately into 4 is happening just because of this float. But can we reduce the float there? Yeah, we could, but that would mean you have to reduce the dimensionality, and that would also mean that the quality of the search will be impacted, because now each of those dimensions are the numbers that we have. Instead of 4 bytes, we could have 1 byte or 2 bytes, and that would mean we are cutting down the memory for a small recall cost. But does that mean we will get the cost benefit that we are looking at? So that's what quantization is about. And quantization, for example, instead of 4 bytes, you could reduce it to 1 byte, but that will have dramatic performance on your recall. Yeah. Then we have a linked list and a stack. Linked list is nodes scattered in memory, where each of that node holds a value plus a pointer to the next. It's like address telling you that, hey, go there. Yeah. Imagine a treasure hunt. Okay, you start with one point and then they give you a clue, and you solve that clue, you go to the next point. Yeah. If you walk the chain, you're going to access a particular element at n by on notation. Yeah, if you were to insert or delete, it's O1, because you know the point where you need to do it. If you have to search for a nth element, it is O of n. But stack, which is like putting a stack of plates on top of each other, you put it on top, you take it from the top. So it's like last in, first out. Yeah, whatever came last goes out first. So it's easier for us to do this because you're only operating with one element there. That's why the big O notation is O of 1 or order of 1. And AI hook, a sequence of tokens, events, conversation history, these are all linked list because you're telling, hey, what conversation was prior to this, what conversation was next to this. All these are linked chains. Yeah, streaming output token is also this pattern. Yeah, you tell, hey, previous token was here with this address, the next token is here with this address. That's how linked list work. And anything that is stack is more in terms of recursive or nested agent execution. When an agent spins up a subtask which spins up another, we are saying, hey, once you finish this, go back to the parent when the child finishes. Yeah, that's the stack that is of last in first out style. And it's all about depth first agent planning, uses one implicitly. We're going to look at this in the coming slides. So we'll park this for now. I know it's not relevant here. Yeah, for PM conversation, how does this make sense? Yeah, rarely we'll talk about linked list, but the trade-off, hey, you need random access versus cheap insertion. Yeah, that kind of decisions will come to us. Here you're going to be asked, what's the max nesting depth before this agent recursion blows up or loops forever? Imagine each agent spinning its own agent and never coming back. Oh my god, that's a huge compute happening, but no results being delivered. So we need to calculate on what's the max nesting depth that will allow for this agent when the recursion happens. And that brings us to queue. We looked at last in first out, wherein we said that, hey, you're stacking a group of plates one on one top of another. That was our stacking, or putting the plates on one top of another. Here is another something called queue. In queue, it's like your people standing in a queue to buy coffee. Whoever comes first will be first served. So they are standing in a queue or a line, okay? And that's what it does. It enqueues at the back. You're adding elements at the back of the queue and dequeuing from the front. It's all O of 1 because there is only one operation. You add from the behind, you dequeue from the front, okay? Continuous batching, virtual LLMs was the key idea. VLLMs is used at inference level where you're trying to batch all the requests coming in and you serve using VLLMs the data. All frontier models use VLLMs to at inference time to deliver the tokens. Okay. What happens when a request comes? It passes through VLLM. VLLM batches the whole request. It sends it to GPUs. Pulls the data from the LLM that's running on the GPUs and gives the response. Okay. So how do you do this batching, static batching, continuous batching, that dramatically improves the performance of a GPU or its utilization by 2 to 4 times? Yeah. Messaging queues like Kafka, Amazon's simple queue system, Celery, they all sit between these services. Okay. So the PM's question is, hey, at peak query per second, so here QPS stands for query per second. At peak query per second, how deep does the queue get? And what's the P95 wait before a generation even starts? Yeah. Because queue wait time is something that's invisible in a time, and we always expect that the moment I submit, it directly goes to the LLM and LLM is giving the response. But in production, what happens? There are hundreds of users trying to access, and then there is a queue that forms. Hey, who needs to be served first and at what pace? Because if the request queue grows larger, these GPUs are bottlenecked because of this request queue. So maybe the GPU's performance is at question, but more importantly, how are we solving for a request queue? Yeah, that's solved using these queue techniques or queue data structures. Imagine there is a queue that's forming A, B, C, D, E, F, G, H. Yeah, GPU will execute in the same sequence A, B, C, D, and so on. Imagine GPU, like we discussed, can handle only 4 requests at a time, where each request is like are a batch that's coming to it. So imagine these are the tokens that it needs to generate: 20, 30, 500, 25. Okay, and imagine that per second it can process around 20, 25 tokens. Yeah, while today's frontier A800 or H100, all of these can do 250 tokens per second. Let's imagine it says 25, for example. So D, B, and A would be completed, and C would still be running at this point in time. Yeah. So for that batch to complete, the GPU will say wait. It will not deliver BCD and allow others to enter the queue. So GPU's performance is low here. Yeah. Though the higher latency for short requests, immediately it's giving a response. The GPU is idle for completed sorts. A, B, C, A, B, D is done. Nothing else has come in. Yeah. Only C is continuing. This is a poor utilization. Okay. That's why it's called static batching, and it's a straggler problem. Yeah, in this straggler problem, the GPU cannot return the batch until the longest request finishes. That is, until C finishes, it cannot return this batch in the response. So one 500 token generation holds 325 token replies as a hostage. It holds them hostage, even though they are served, it holds them hostage and says you cannot go. And that's all through continuous batching. Imagine there is again ABCD in the queue. A's request is a smaller token count, for example, 25 tokens. B or C or D is large. The moment A finishes and E joins the batch, now it is B, C, D, E that is being solved for by the GPU. So what happens here? LLMs generate one token at a time. Okay, every step of the engine asks, hey, which request still need the next token? So if E joins, E will not wait for D to finish. It will immediately join the queue if A has finished. Yeah. So if you understand, GPUs are purchased for dollars, and if they are sitting idle, they don't serve anybody. So GPUs have to be continuously used or utilized. Okay, and continuous batching lifts that utilization from 40 to 80 to 95%. Ideally, GPUs are utilized around 60 to 75%. Rest of it is for peak hour planning, it's for latency, it's for throughput. There are multiple factors involved, so utilization never goes to 90-95%. If I understand it right, it usually stays between 70-75%. Yeah. So the same hardware serves far more requests, and each request becomes much more cheaper when we do continuous batching. Yeah, and this is where serving architecture directly affects cost per token, a line item, not an implementation detail. Yeah. And we were talking about VLLM. Yeah, what is this LLMs that are helping generate so much data? Okay, we earlier saw that, hey, if it is fixed batches, the the performance is taking a hit. So what we saw was VLLMs were introduced that highly improved the efficiency of the GPU using continuous batching. Yeah. The result of this was that the GPU utilization went high, latency reduced, more concurrent users started coming on, and the cost per generated token went lower and lower. Yeah. Just changing this serving layer or the inference layer sometimes yields 2 to 4 times higher throughput without changing the model also. So what is the wrapper around your LLM also makes a big difference, because it's helping you manage this queues. Okay, and queues are sometimes are the bottleneck in the whole pipeline. Okay, without a queue, if the embedding is slow or crashes, uploads are delayed or failed. But if you with the queue, if you add, it adds a layer of bottleneck, but it also helps you serve a purpose like processing those data or execution or calculations independently. We are going to look this in the next one. So imagine if the system had 4 GPUs and each GPU can process 25 requests per second, and then there is a total capacity of 100 query per second, which is 4 GPUs into 25 requests, which is 100 queries per second. Yeah, or requests per second. Then the traffic spikes. For example, at 10 o'clock, there are 80 requests coming in and the capacity is 100. So it is immediately served. But at 10:10, there is 120 queries per second coming in and only 100 is the capacity. So for every second, okay, for every second, 20 queries are being held hostage. So at the end of 10 seconds, you will see 200 will be queued. Okay, imagine at the end of 20th second, 150 more queries arrive, then it will be 1200. You see now, with incoming queries per second increasing, the queue is also increasing. Yeah, that's what we are saying. The queue keeps growing because requests arrive faster than the GPUs can train them. For PM, the question is, at peak traffic, does the queue reach 20 requests or 2000 or 5000? Because queue depth is the early warning that the system is overloaded. Yeah, before anybody files a latency bug saying that, hey, I submitted a request but it is only coming after 3 seconds, 5 seconds, 10 seconds, before anybody can raise, our queue depth can immediately tell us whether we are there or not in terms of latency. And one important factor is the P95 wait time. If you understand what is P95, P95 is the percentile. It tells how many of the total users are able to get the required performance in the required time. So P95 is used to measure the system latency of response times. Yeah, we know that when user clicks send, a query is sent to the queue. It is waiting in that if there are only limited GPUs. Once it goes to GPU, then GPU starts generation and then a response comes. Yeah, imagine this case. There are 90 requests coming in. There is 50 millisecond performance of these 90 requests. Good. Another 5 requests come, 300 millisecond. Another 5 requests come, but this time they take 3 seconds. Your average could be 220 milliseconds, but the P95 is 3 seconds because the last 5 requests took 3 seconds. The 95 percentile is at 3 seconds, not at 220 milliseconds. That's why P95 queue time is very important. And in the demo, we'll always see that it achieves 50 milliseconds, 10 milliseconds and all. The repeatability, or how many times can we maintain the same performance, matters a lot in production. Okay, because one user means queue wait time is 0 milliseconds, but in production at 5000 concurrent users means queue wait time can go to 2.8 seconds, and generation time is still 700 milliseconds. Yeah, the users will say AI is slow. The model isn't slow, but the queue is. Okay, so that's why we need to manage all this. So we have to stop asking as a one question, how fast is the model? Instead, we need to understand the whole entire flow and ask, hey, what was the peak query per second? Were there concurrent requests per GPU happening? What was the average and P95 queue time? And how often have we breached the SLO, which is the service level objective? We're going to look at what is SLO. And then we say, hey, is it auto scaling or throttling? And finally, is the queue wait time or generation the dominant term that is being used? Okay. All this tells us that we as PMs have understood what's going behind the black box. If we do not, engineers will be at a loss of understanding what to build, how to scale it in the first place. And somewhere 1 week or maybe one day down the line, when users start using it, they'll start raising bugs. Hey, I don't see the performance. I see a lot of latency. I'm not getting the required responses in time. There is a bad user experience happening in the end. That's why product managers need to understand this. Like I said, service level objective, we need to understand the different types. Okay, we know SLA, service level agreement. It's a contractual commitment given by us typically to customers, and we say that if we breach that, we'll offer you some penalties. For example, we say 99.9% uptime guaranteed. Yeah, whereas SLO is a objectives that defines what will be, how will we try to target it. Okay, this is more like a target. So we say that, hey, P95 latency should be under 2 seconds always. The moment somebody types a query and hits enter, this whole cycle of taking it into the queue, waiting in the queue, getting the GPU's generation started, calculating the response, and hitting it back to the UI, everything should happen under 2 seconds, for example. Yeah, that could be our service level objective. This is like the target. But what is actually happening? That's the service level indicator, SLIs. That helps us understand the measured metric. Actual P95 latency could be 1.8 seconds. Yeah. So this is the reality. This is our target. This is what is committed to the customers. Okay. This is always high because there are penalties involved. This should be considered as a goal. This should be always monitored. Okay. That brings us to hash table. So what is a hash table? Uh, Hash table is a table where when a key comes, it's hashed using the hash function, and it's stored as a value. And instead of us calculating it every time, we look up to these calculated values and use them. Yeah, what's the benefit? It's helping us run things faster, and we don't have to recalculate the values again and again or search for them again and again. The mental model looks like something like a code check. You don't have to search for the same uh, hook or a code again and again in the racks. If you had the ticket number, If you had the ticket number, it'll send you straight to the right hook in the racks. So that's how hash table helps us. uh, how is this important? Because it reuses the computed key value tensor for past tokens instead of recomputing. If you had to recompute and then do that, you take almost n square as the quadratic O notation. But instead of that, since you have already calculated it, you don't have to recalculate it. All the data are stored in cache, and it pulls from there, attaches this token, and sends the answer. Yeah. It also helps in prompt or response caching, because a trained paid model uh, will become a free dictionary hit. That is, if you hash the prompt, it will return the stored answer instantly, and that will turn that dollar model into literally free, because you are not wasting any time to regenerate the existing tokens. Yeah, that's how the dollar values are saved. And if you look at feature stores, a low latency feature can be used to inference much faster. Yeah, so the inference speed also turns faster if you have hashed the whole data. Finally comes the deduplication. If you have used hash functions, you will understand that for every unique data, the hash function ensures that the value is very unique. So deduplication is also much faster using hash tables. Data cleanup, near dedup detection, near duplicate detection, all this happens via mini hash as a function. So as a PM, we need to ask, hey, what's our cache hit rate? How many times are we hitting the cache that we have already stored? Because that will help us save in latency and dollars. A 40% exact match hit rate on an expensive model is a line item. You have to put it in your requirement saying that, hey, improve the caching. Every time a question is being asked, the same question is asked again and again, we need to ensure that we take it from the cache, not regenerate the whole answer again and again. Yeah, this is why the first token is slow, because you have to generate it, store it, and then work on the others. But when you go with the later tokens, they are much faster, because you now know the first position, you have pre-calculated all the other tokens. Yeah, and that's why long conversations eat a lot of GPU memory. Yeah, because you have to do this again and again and again. Yeah. So we can look at an example here that we are looking at. Imagine you had Alice as a word coming in, you hash it and store it as 95, Bob as 88, and so on. Now, if you had to get a ticket for 257, you show that 257 number, it immediately goes there. Okay, so the average lookup that you're doing is of the order of 1. It's almost equally fast at 10 tries, 10 tries, or 10 million, or 10 billion, or 10 trillion also, because the order of search is only 0 of 1. Yeah, because without hash table, you'll have to search across 10,000, 1 million or so, because the order of search will be O of n, which is linear, like an array. But since we have hashed the tables, we know the exact position, we can go off immediately. Yeah. So the math that you need to look at is this. Okay, if there are 100 requests coming, 40 is served from cache and 60 is sent to the LLM. So every request that goes to LLM is the cost, 40 is the saving. Yeah, so cache hit rate is 40%. 40 into 0.05 is approximately $2, because 0.05 is the number of requests are the cost of dollar for each request that is going to LLM. Now, since this dollar is going to cache and being served from there, we are saving approximately $2. Yeah, so hash tables help us hit or achieve the higher hit rates, which basically means faster responses, lower GPU usage, lower infrastructure cost, better user experience. Yeah, lower infrastructure cost because lower GPU usage, better user experience because faster responses. Yeah. Then tree, which is a hierarchy. If you know how a tree structure looks like, it looks something like this. There is a school, then there are subjects, and some of these subjects have sub-subjects. For example, science is a subject, but it has physics and chemistry as a sub-subject to it. Okay, that's a tree for us. So org chart, a family tree, a folder hierarchy in our laptop, everything follows a tree structure for us. Why is this important? Because tokenizers merge trees. We're going to look at this in the upcoming slides. For example, binary pair encoding that we use to build vocabularies uses this merge rules to build the whole embedding. Yeah, and that's why token costs are not equal to character counts. Number of characters does not mean that the character counts. Sometimes a big word can have smaller token count. Sometimes a smaller word can have a bigger token count as well. Okay, it helps in decision trees and gradient boost techniques, XGBoost, LightGBM, gradient boost machines. Still, the best default for tabular prediction. Yeah, tree of thought. An LLM explores a tree of candidate reasoning paths and prunes. This is very important because we are going to look at in algorithms as well. When we give an LLM a big reasoning task, it will create a parallel reasoning tasks, and it will say what's the best approach that I could solve this problem with, and it will try to rate itself on those trees, and it will come back and say that, hey, I think I need to follow the this particular branch, and go from there. So a tree of candidate reasoning is important because the cost will be associated accordingly. Yeah, we're going to look at ANNs later, and we'll come to that. So the PM question will be that, hey, if I had uh, a tree structure, a tree based retrieval implemented versus a graph based retrieval, what will be my recall versus latency trade that I'm going to do? Yeah, the vocabulary starts here, the decision lands in one of our future sessions. What we are asking is, hey, if I implement this framework versus the other framework or data structure, what would be my recall versus latency? Because not everything can be achieved through the same algorithm. Some algorithms are good at one thing, the other algorithms are good at another thing. Okay, so imagine there were documents like college and photos and assignments notes, and then there are folder specific ones. Every node will have one parent except the root one, which is documents will not have a parent. And zero or more children, for example, the last one can have a zero or more children. For example, college has 2 children. Okay, unlike a graph, a tree has no cycles. That is, 2025 is not associated with nodes here. Photos is not associated with colleges. We only know that photos is the child of documents. Yeah, a family tree, an org chart, the folder structure on our laptop are all of the same examples, just like we saw. Imagine a tree structure like this, and you are trying to find 65 as the number. Yeah, we start from 50, and we know that 65 is greater than 50, so we go this route. Then we know that, hey, 65 is less than 70, then we go this route. We know that 65 is greater than 60, then we go this route. So it takes 4 steps. Yeah, what are we trying to see? A balanced search tree eliminates half the remaining possibilities at each step. And we looked at binary search, which is of the order of O log n, order of log n. Okay, that's the growth rate that we are looking at. So 6 places trees run your AI stack. We are looking at tokenizers. Imagine there is a word called unbelievable. Binary pair encoding, what it will do, it will create it into 3 tokens. Unbelievable. Because believe is a word, believing is a word, believer is a word. So INGERABLE are separate words because BILEV is being stored separately. Okay. Pricing is per token, not per characters. So 2 words of equal length can cost very differently. Okay. And decision trees. Imagine if income is greater than 10 lakh, give a credit of $700 or rupees, and then approve. If they have both income and credit score, then approve. Sorry, here is credit is not about giving credit, but more of the credit score. Imagine the credit score of this user is 700, then approve it. So decision trees are used there when you have if else conditions to be used. Trees of thoughts, for example, LLM explores several reasoning branches and keeps the best. It's like trying to maintain multiple routes through a maze. Tree based search, when 100 million embeddings are created, a tree structure arrives there, and similar vectors are known, well known, and it will help us narrow down on what embeddings to, or what vectors to refer to. Okay, abstract tree syntaxes, for example, if you had to teach x is equal to a plus b into c, it becomes a tree structure. A model can read this and create a tree structure to understand the expressions and control flows. Maybe we'll look into one of these examples in the future. Okay, b trees in databases, select star from this blah blah blah, doesn't scan every row, it only uses a b tree index. Maybe in one of the future sessions we'll look at this. Okay, and retrieval is also a little different. Tree based is faster, less memory, may miss some of the neighbors. Graph based HNSW, we will look at HNSW in one of the future slides, so let's park it there. Graph based has a higher recall, but it requires more memory, slighter higher latency. And when we need lower latency, we'll always go for tree. Highest quality for RAG is always graph. Okay, we are going to look at it. Why is this so in one of the future slides? Okay, binary pair encoding. How does this tokenization technique actually work? That's what we are looking at here. So imagine BPE is nothing but a tokenization algorithm that splits text into tokens before a model processor. Okay, a token may be a whole word, part of the word, punctuation, or a space. It could be any of that. Okay, so how does BPE build a vocabulary? It starts with characters. For example, if you have low or lower, if low is already put in the embedding, then ER will be stored separately. Yeah, and newest, EST will become a separate thing. So it repeats this process. It starts with lowest, smallest character, and then looks at the neighboring characters and say, if I say low, low will be indexed. Then I get W. Since low was there, low is a very unique word, so it does that. But lower, low is already done, R is a separate word, so it will store it separately. And that's why vocabulary already contains some words like playing, player, and separately. So play will become a separate word, ing will become a separate word, and play space r will become a separate word, not playing, because then we will need fewer tokens. Not every token has to be uh, uh, put into the embedding in a vector space. Okay, why it's needed? Computers understand numbers, not words. We know this. We don't have to come here. So unbelievable becomes unbelievable. Okay, 3. Uh, if it was unbelieving, unbelieve ing, unbeliever, believer, believe plus er. Okay. So why is tokenization a pricing question? Because the more the number of tokens that we create, the larger the embedding size or the embedding model, and our vector space also goes huge. Okay, English has millions of possible words. Instead of storing every word, BPE stores common pieces, dramatically reducing the vocabulary size while still representing almost every word. Yeah. Why byte pair? Why do we call it byte pair encoding? Yeah. So the original algorithm compressed files by repeatedly replacing the common pair of bytes with a new symbol. Two words. That's how it started. And LLM tokenizers adapted this idea, merged repeatedly thousands of times, and they landed on a vocabulary of roughly 30,000 to 100,000 tokens. Instead of millions of possible words, we are now looking at 30,000 to 100,000 tokens. Okay, what's the consequence of this? LLMs are charged by tokens and not words. We know this. Whenever we start using ChatGPT, Claude, Gemini, or any of these large LLMs or frontier models, we see that they are charging us by tokens, and this is very important to understand. For that, one long word may cost many times more than a short one. So always generating crisp answers as a response to users will save you more tokens from the LLMs, and in turn it will save you a lot of cost. So that brings us to graph. So what is a graph? A graph is nothing but interconnection of nodes through edges. Imagine there are nodes or vertices that are represented by actual data and edges by their relationships. We can create a nice looking graph, something like this. For example, these are people in a social network. We can create a graph saying that this person knows this person, and this person knows these two people, and these individuals know various other people. So like that we can create a graph, and they can have cyclic natures. That is, this person knows this person, this person knows this person, this person knows this person. Unless like a tree, which is a directed acyclic graph, that's what they call it, DAG, directed acyclic graph. Your graph is a cyclic graph, as in it's cyclic in nature. Okay, it's stored as adjacency lists or matrices. That's how it's stored. And the mental model is a subway map, a social network, or a citation web, where one citation refers to another, one citation refers to other. There could be cyclic citations as well. Where are these used? These are used in knowledge graphs or graph racks. uh, Very interestingly, like in the last slide we read, the best of the RAG applications are built on graphs. We are going to look at more of this in detail in the upcoming slides. Okay, retrieval traverses relationships instead of just matching vectors. Okay, it's better for multi-hop questions. For example, if you ask, hey, what was the revenue of this particular department in 2022 uh, when these were the products sold? So there are three things that we need to filter by, and so on. So graphs provide us uh, better answering capabilities on there. Agent workflow engines. LangGraph is literally a state graph. When you design an agent, you're actually drawing a graph. You're saying that, hey, do this as a sequence, and then do these. So that agent is nothing but a graph. And HNSW is a indexing system that you use to search for data that has been indexed as a graph. Okay, it's a multi-layer graph. You greedily walk in with the order of log n, and this makes it possible to search over 100 million vectors in 20 milliseconds. Yeah, this HNSW, we'll keep talking about this. This is hierarchical navigable small world. This is what permits search at scale in vector databases. We're going to look at computation graphs also, and how they use PyTorch term frequency to represent a model for auto differentiation in the future. This graph, what do I call, data structure, is used by Pinecone, VV8, pgvector, which are all graph databases. FISE, LangGraph, Airflow, all of these use graph structure under the hood. Then the architecture call that a PM needs to take or discuss with engineering team. Hey, is this a workflow or an agent? Where the model chooses the path. Deterministic graph or learned traversal is one of the most important decisions you will ever make. Okay, so if you need very strong answers, then you will have to go with deterministic graph versus learned traversal. Yeah. Heap, the last of the data structures that we are going to look at, it is a heap. Heap is nothing but a priority queue. That is, we looked at queue. Queue is nothing but first in, first out. And in priority queue, there is a small difference that we take top k that we have put in. Okay, a tree-shaped structure keeping the min-max instantly reachable. Okay, and the order with which we can do peak is order of 1. Insert or pop is inserting the record or removing it out is log n, because you will have to go with half the traversal every time you go deeper and deeper. Okay, the number that matters, a top k of n items, is O log n k. Yeah, because we are saying n times we'll have the search happening, and you need to get the top k out of that. Okay, much cheaper than a full sorting at O n log n, which is way more, because you're looking at n items instead of just the top k. Okay, so it's fully it's much cheaper than the full sorting. And the mental model is a hospital triage. You always pull the most urgent patient next without sorting the whole waiting room. Yeah, you know that somebody has fever, you put him in the queue, you see somebody coming urgently with a lot of pain, unable to bear it, you'll triage him first. Okay, so heap or priority queue is what hospitals use. Okay, if you're going to build a model on some prioritization technique, I would recommend you look at heap or priority queue based on certain parameters, how you can do that. Okay, task schedulers, beam search, Dijkstra and A star for agent path planning, all of these use heap or priority queues. Okay, we're going to look at these in detail in the agent workflows, and when we are going to go there. The AI hook is, hey, the top k retrieval in a heap operation. That is, every rag retrieval that we are trying to do, every recommendation of top n, every ranker shortlist is all a top k framework or a model. Okay, so the PM's question is going to be, what's k and is k tuned for recall or cost? Bigger k means more context to the LLM, better recall, but more tokens, more dollars, more latency. K is a dial you own. When the number of documents from the RAG need to be retrieved, it retrieves the top k documents. So you as a product manager need to decide how many of them should be retrieved and sent back to the LLM to give a response. We look at the whole retrieval augmented generation framework in one of the coming sessions. But in simple words, RAG helps you pull the right documents from the vector database or vector DB and give those top k documents to LLM to figure out what's the right response that needs to be given. Okay, if the number of top k documents is more, it means more context to the LLM, but better recall, because it has given all the required documents, but that also means at the same time more tokens, more dollars, more latency. Yeah, so what's the optimal number that you need to give? What's the sweet spot, if I can say so, that you can hit to get the right latency, cost, and and the value? Here's the cheat card. Okay, take a screenshot of this if required, but this is what will drive all of the AI track that we're going to look at for product managers, for especially based on the computer science foundations that we have done so far. Yeah, array, access, search, insert, and delete are of these orders. We know that search, insert, and delete is of the order of O of n, and the AI things that we need to remember is that these are used in tensors, and GPU loves continuity or contiguity. Coalesced array vectors are better for GPU because everything is in the sequence of the addresses and it's faster to access them. Okay, linked list is of the order of n for access and search, order of 1 if you want to insert and delete, because you have to know the address where you want to insert or delete. But to access, you'll have to navigate from the 0 till that nth element until you find that element. Okay, these are sequences, and streaming tokens, your chat conversation history are all linked lists. Then we looked at stack, which is of the order of n for access and search, just like linked list, because top, you put it from the top, you remove it from the top. But if you had to access and search a particular element, you have to go through all the elements, so it is order of n. Insert and delete is order of 1 because you insert on the top and remove it from the top. All your recursion, agent subtasks, undoing a particular activity in an application are all based on stack. So when you type your words on a Word document and you do undo, you're actually using a stack there. Then we have queues. Queues is nothing but first in, first out data structures. So the order of n is used for search and access, because if you have to have access to a particular element, you have to start from somewhere and go until that element. That is a linear this, so it is of the order of n. Insert and delete are of the order of 1. Inference batching, service decoupling, all of these are used in queue. Hash table we looked at, order of 1 on an average, because it's a key value pair cache that we are maintaining, and given on the element's address, we always know where to find the element, so it is always the order of 1. A tree, order of log n, because we are always splitting the tree into one or more branches, and we only have to go half the branches every time we go in one particular direction. So tokenizer, byte pair encoding, your gradient boost trees, your tree of thoughts, your ANNs are all dependent on tree. Then we looked at graphs. It's varies, access and search, but the order of insert is 1, given that you know the edge or the node. And delete varies because again you'll have to traverse depending on the kind of framework that you have used. Yeah, so knowledge graphs, graph rags, lang graphs, HNSWs are all using graphs. All your vector databases use graphs for rag. Heap, we looked at how the priority queues are built. It's of the order of 1 for accessing an element because it's faster, but when you want to search, it's order of n because you have to go through all the elements. Then it's order of log n for insert and delete, because you'll have it's almost like a tree, so you'll have to go through all of those elements to put it in the right place. And top gate retrieval, schedulers, beam search all use this data structure, which is heap.